Back with another video of my speaker project. This time it's going to be mostly theory because I want to go through, I want to draw out exactly what I'm aiming to do here so that I can calculate the exact value of capacitor I need to put in series with the tweeter. And once I get that, I'll figure out how to install the new tweeter in the existing enclosure. And as far as installing this, the mechanical part here, I think I'm going to turn this upside down, mark out the hole pattern, drill the holes straight through, and then using some machine screws and washers and some nuts, I'm going to mount it from the inside like so, because it fits really nicely like that. Because if I end up mounting it from the outside, see this, the compression driver itself is wider, the diameter of this is wider than the width of the horn. So if I cut a hole to fit the compression driver through, when the horn rested in there, there'd still be a gap around it, and I really can't separate the horn itself from the compression driver and then mount the compression driver from the front and screw the horn in from the back, because this baffle doesn't, it's not removable. And I have no way to get in there with a screwdriver and screw these in from this side, from the opening here. I can't do it. So I don't care how this looks. The opening is just wide. That's just right, and that'll work just fine. I don't care that it looks kind of funky. I'll use a Sharpie pen and make the wood black right there. It'll look kind of cool. It looks like a keyhole. But before I even get to that point, I need to figure out the value of series capacitor. Now this is going to be interesting. I want to go through the theory of this. Let me pop this on the tripod here. I want to go through the theory because I don't like just to look. I don't like to look in a book and have some book say, well, pick this value and do it this way or do it that way, because I want to know how it's done. And I think going through and explaining the theory might be helpful to others, and it's helpful to me because if I'm doing something incorrectly, someone points it out to me, then I learn something. So, that having been said, let's get started. We'll get started with just a diagram of what we're doing here. I have a woofer, and we'll draw this as the horn tweeter, and I've got positive and negative inputs. The woofer is directly wired without a crossover. The woofer itself is going to have a natural crossover point all by itself, somewhere between 1 and 8 kilohertz, something like that. We got to figure out where that point is. That's going to be the first experiment. Now, what I'm going to do is, the existing piezo tweeter did not have a crossover. It was directly wired, and we can't get away with that anymore. With a compression driver, we need a crossover. The simplest crossover is a series capacitor. Like that. This tweeter is 8 ohms. So the challenge is what capacitor to use. But it's not that simple. There's a couple of complicating factors. It just occurred to me, so I'm going to have to redraw this. It's not, this is interesting. So what's going to happen is the tweeter, if we pick the right capacitor, the tweeter crossover frequency will be the same as the woofer, see? And then so together they sum up to form a flat line of a frequency response. So that's picking the right capacitor. However, let's start out just talking about how to pick the right capacitor. You could go to the web and find a chart somewhere, I'm sure, but let's talk about how to run those numbers yourself. Before I do that, though, and you're going to find out, we need to know what we need to know to pick the right capacitor. We need to know the impedance, the nominal impedance of the device, of the tweeter itself, 8 ohms. But it's actually not going to be, here's what I'm hesitating, it's not going to be 8 ohms, and here's why. It's not enough just to pick the right crossover, the right capacitor for the crossover frequency. There's another factor to be considered, and that is the sound pressure level of this horn tweeter is naturally going to be, this is going to be more efficient than the woofer. So not only do we have to match this tweeter in crossover, we have to match the acoustic output to that of the woofer. So in other words, if we were to do this right here, just had the right capacitor, and here's what it would look like. The woofer would, this is acoustic output right here, SPL, sound pressure levels. But the tweeter, would be much higher in level like that, because it's much, tweeter's much more efficient than a woofer. So summed together, it would look like, it would be horrible. The speaker would be really bright, would sound like it had no bass frequency. So there's another thing we have to do besides the crossover. We have to adjust the level. Now, one of the ways you can do it is to add a series resistor. But I want the ability to adjust the level. So what I did, I want to adjust it to taste, because I like to, when I'm playing, these speakers are for playing drums, and I actually like to turn down the frequency, down the high frequencies. I want more mids and bass. So I want the ability to adjust the level kind of as we go. So I purchased some L pads. L pads are for this purpose. And I don't want to get into too much detail on an L pad, but what it looks like, if I remember this, I'm going to draw how this is going to work. We're going to have our capacitor, that's our crossover. We're going to go into the L pad, which is going to look like this. Is that right? And then this is going to go into the speaker itself, like that. Did I get that right? Man, it's been a while since I've done. But before you take me my word at it right here, here's what the L pad is right there. It has three terminals to it, and I forget. They're labeled L 1, 2, and 3, and I forget which is which. But it doesn't matter. Let me show you what this effectively does. For the purpose of picking a crossover frequency, I don't need. I'm gonna have to look this up and remember how this works. But what it is this L pad will always be 8 ohms. It's an 8 ohm L pad, because no matter where you would turn this knob, and no matter where these Okay, so what I was saying, I heard a noise and I had to go check it out. It was my dog walking around upstairs, creeping around. So no matter where the wiper is right here, these two wipers, when you rotate this, they kind of move up and down. But here's the point, no matter where you rotate them, the L pad will always look like, it will always appear to be an 8 ohm resistor in parallel with the tweeter, which is also, in this case, 8 ohms. So as you rotate this knob and these wipers move up and down, it will effectively change the amount of voltage that reaches the tweeter and raise and lower the level of the tweeter, but this always remains an 8 ohm resistor, so you can count on this collective load remaining constant or the same, relatively the same. So what we can do is we can simulate the L pad and the tweeter as two 8 ohm resistors in parallel, or one 4 ohm resistor, like that. Now our circuit we have to deal with is a capacitor, right, and a 4 ohm resistor. So that's the important thing to note, is that we're not dealing with, even though the tweeter's 8 ohms, we're really dealing with a 4 ohm load, because the L pad is going to be in there in parallel with the tweeter. So that having been said, let's talk about how to, and we're going to also verify all this by experiment. So let me get back to my diagram. Let's talk about how to figure out what your capacitor should be. Now, I'm going to have to, okay, let's go ahead and draw this. So this is 4 ohms. Now this capacitor is going to act like, to an AC signal, it's going to act like a resistor, so to speak, at each different frequency. It's called capacitive reactance, but it's going to look like resistance to the AC. And the resistance, or the capacitive reactance, I'm going to call it XC, is going to be equal to 1 over 2 pi times the frequency times the capacitance. The 3 dB point, okay, let me draw my diagram here. Here's the woofer. The negative 3 dB point. Here's the tweeter. Woofer. This frequency right here, I'm going to determine it where it is on the woofer experimentally, but I want to just first, for the sake of how to determine the capacitance here, let's say it's 1K, 1 kilohertz. So let's say we've determined the woofer to be the negative 3D at 1 kilohertz. That means we want the tweeter to have a negative 3D at 1 dB point at 1 kilohertz. So now we know the F. How do we determine what capacitance to use? Well, this negative 3 dB point is the half power point. And this half power point is when the reactance here equals to 4 ohms. Because if this is effectively 4 ohm resistor in series with that, then you're always going to have an equal amount of power dissipated by this resistor and that resistor, because they're the same resistance. So if an equal amount of power is dissipated by that versus that, and then you're going to be down at your negative 3 dB point, or your half power point. So, how do we determine what capacitance it takes to achieve 4 ohms at 1 kilohertz? It's pretty simple. 4 ohms equals 1 over 2 pi times 1,000, that's 1 kilohertz, times C. So let's just bring the C up and the 4 down, right? So C equals 1 over 2 pi, 1,000, times 4. right? I mean, that's it. Look at my calculator. I can't do this in my head. All right. 1 divided by 2 equals divided by pi is what? 3.14159 equals divided by 1,000 divided by 4. And that is going to be 40 microfarad. 40. 39.7. Let me just verify that. 1 divided by 8 divided by 3.1459 divided by 1,000 is the frequency, and that is, yes, that's 40 microfarad. So that's how it's done. So that's the equation. The equation is capacitor is going to be equal to 1 over 2 pi times the frequency of your crossover FRE frequency times the impedance, I'm going to call it R, of your load, which is your speaker nominal speaker impedance. So that's how it's done. So before I can figure out what capacitance I need to figure out the crossover point of the woofer, where it naturally rolls off to minus 3 dB, and I'm going to have to do that experimentally. And that is the next step before we move on. So, what to do? Well, I am going to have to hook up. I have to get this thing hooked up. Let me hit pause. No need to watch that. I'm going to have to cover this hole up. Screw the woofer in. Cover that up because I don't want the hole where the old tweeter came out, to affect the frequency response of the woofer. So this needs to be covered, and I need to hook this up to a signal generator and an amplifier, and then just start sweeping it and figuring out where negative 3 dB is. Alright, what I've got here is I have my function generator on sine wave. It's 5 kilohertz. I've got that inputting into a standard audio amplifier, and the output of the audio amplifier, the speakers wires go directly into the speaker. The tweeter is not hooked up, it's disconnected internally. I just have it screwed in here so I can get an accurate frequency response of the woofer. So the only thing working is the woofer right now. So what I'm going to do is just see, based on listening alone, where I can sense the speaker rolling off. Okay, start out at 1K. So we'll go higher. There's a increase in level right there. Whoa, that's so the woofer naturally gets louder. Okay, now we're back at 3 kilohertz. We're back to about the level where it was at 1K. Okay, now it's getting quieter, right? Okay, it's really starting to get quiet right there. You can see it's rolling off. And between 8 and 10, there's nothing left. Okay, so if we go back down to 3, somewhere around 4 to 5 kilohertz, it seems like it's about half at the acoustic level it is as it is around 1 kilohertz. 1, 4, 5. That's about half. 4 to 5. That's just listening. So I'd say the negative 3 dB point is anywhere from 4 to 5 kilohertz just by listening alone. But I'm going to go ahead and try to test it. Although I don't really have a good way to do it other than I do have a decibel meter. So I'm going to go ahead and grab that. I think it's upstairs. Hang on a second. Okay, got it. I don't know why I called the thing a decibel meter. There's no such thing. You don't measure. Decibels is not something you measure. I have this Sony not voice recorder. It's a field recorder. Excellent. Good flat frequency response from below 20 hertz to above 20 kilohertz. And built into it, it has a decibel scale for sound pressure. And that'll work. This is a good enough instrument to. There we go. So I hit record, and you can see the level meters, the left and right. And on the right hand side, it actually gives you a readout. It's all relative, but I'll be able to tell the difference between 3 dBs in level using this. And so what I'm going to do is I'd like to have it as close as possible to the center. Okay, I know what I'm going to do. I got to grab a piece of wood. This is all makeshift. Doesn't have to be. It doesn't have to be anywhere close to being precise. Okay. I'm going to lay this right there. These are omnidirectional microphones. I actually want to be able to see I want to be able to see the readout as I change the frequency. So let me bring the camera over here. So I'm going to start sweeping. Isn't this goofy? I really want to hang it upside down and let it, but I'm just going to, this is good enough. Okay. Can't really see the readout because of the reflection. Get that out of the way. Alright, now let me turn up the... Alright, let me start out. I'm going to start out at... I'm going to start out at 1K. 1K. Now I'm getting a reading of negative 6 dBs. I'm going to use 1K as my reference. And I should get, at some point, I want to get down to about negative 9, where it's, and I'll do a couple measurements to see if it's repeatable. It gets louder there. Okay, there's where it starts going down, watch. Okay, right there where it starts going down, that's 4, right there, that's 4 kilohertz. 2, 6. So I need to get to -9, and I'm there, and that's exactly at 4 kilohertz. It's actually -13 now. Got a -8 at 3.2 kilohertz. I get -13 at 4 kilohertz. So relative to 1 kilohertz, it's somewhere between 3 and 4K. Let me turn this down. Relative to, I just picked 1K as a reference point, but relatively speaking, this thing, the -3 dB point is between 3 and 4 kilohertz. So I'm going to go with 4 kilohertz. And then let me get rid of this stuff, and then I'll take, let me take this speaker away, and then we'll do the numbers and find out what capacitor to use. All right, so here's the deal. My crossover frequency, I'm going to go with 4 kilohertz. And we know that our speaker load, because of the L pad, is going to be 4 ohms. So I got to find my calculator again, what capacitor in microfarads do we need? Okay, it's going to be C equals 1 over 2 pi times 4,000 times 4 equals 1 divided by 2 divided by 3.14159 divided by 4,000 divided by 4 equals 9.9, 10 microfarads. If you can see that or not. I'm going to run this number again. That'd be good because I have some 10s on hand. I know that. I bought a mess of them for a project a while back. 9.9. We'd run that again. 1 divided by 2 equals divided by 3.14 equals divided by 4,000 equals divided by 4 equals 1, 2, 3, 1, 2, 3, 9.9. It's 10 microfarads. I have them. So with 10, again, if things work out with 10 microfarads, with the L pad hooked up, eight ohm speaker, 8 ohm L pad, at 4K, the XC. Now we know that this whole mess right here is going to be 4 ohms right there. So we can just redoing this. We know it's going to be 4 ohms, roughly. It's nominal. Changes with frequency a tad bit. But our XC right here, just to rerun the numbers, it's going to be 1 over 2 pi FC. And at our crossover frequency of 4K, and our capacitor of, I'm just doing it in reverse to double check my numbers, 10 microfarads. That's going to be 1 divided by 2 divided by 3.14 divided by 4,000 divided by 0.0000001. Did I do that right? I missed it by a decimal. Oh, damn, it's not. I always do that wrong. 10 microfarads equals 0.00001. Okay, I did. I got it off by 1. Okay. Oh boy, I'll try it again. Make sure I got this camera on. Okay. 1 divided by 2 divided by 3.14 divided by 4,000 divided by 0.00001 is 3.98. So 4 ohms. So we'd have 4 ohms across our capacitor, 4 ohms across our load, and which should be the negative 3 dB point of the tweeter. Let's test it. How am I going to test that? Okay. Get the tweeter. And I need to change batteries on the camera. Stand by. Okay, fresh battery in the camera. Alright. I have a 10 microfarad 450 volt. Voltage is not that critical here. The way we're going to test this, I'm running out of paper. So I want to test to see that really is, when I hook that capacitor up in series, that it really truly is my negative 3 dB point. Here's how we're going to do it. I am going to hook up the L pad. Now, you know, I'm going to have to. I don't even know how to hook up the L pad right now because they didn't come with a schematic. I gotta look up. It's been a long time since I dealt with it. I don't know which pin number is which. I know how they work, but so what I'm going to do. All I care about is there's a 4 ohm load, and the problem is these are 8 ohms. So I'm going to hook up, just for testing purposes, 2 of these tweeters in parallel, like that, and that'll give me a 4 ohms because they're each 8 ohms, right? So I'm going to hook these 2 up in parallel. Let's go ahead and get that done. Here's the other one, and I'm only hooking them up in parallel to achieve 4 ohms. And now I'm just going to draw them as a resistor right now. 4 ohms. So here's how I'm going to test. Going to have like a switch right here. And on one side of the switch, I'll have a signal generator right there. Okay. Like that. So on one side of the switch, I'm going to have my 10 microfarad capacitor in series with the 4 ohm tweeter. When the switch goes in the other direction, it's going to be a straight wire that bypasses the capacitor. This signal generator, I'm going to run some frequencies. I'm going to like 10K, 8K, 5K, 4K, which is what I designed it for, and we'll say 1K. And what we should see is at 10K, I'm going to say position 1 and position 2. 1, 2. Okay, 1 is with cap, 2 is no cap. So at 10K, this capacitor should have little to no effect on reducing the output. So when I go between position 1 and position 2, it should be the same acoustic level on the output. It should have little to no effect. But as we get lower in frequency, particularly down at the crossover frequency, when I go between the capacitor and when I go to the straight wire, when I go down to the straight wire, the level should go up. Because the capacitor, when I'm at the capacitor side, it should be cutting the level down in half. So I'm just going to take some measurements like that to verify that I'm going to actually have to have these tweeters facing up when I do that. So that's how I'm going to verify. So when I get down to 4K, I'm going to hope that when I go from position 1 to position 2, that I have a plus 3 dB gain in acoustic output at 4K. Is that what I designed my, yeah. I'm already forgetting. Yes, I designed it for 4K. Sorry. So that's the test. That's the test mechanism for this. Go ahead and get it hooked up. Okay, this is pretty cool. I got this thing hooked up. Let me take this off the tripod. So I've got the capacitor. Let me show you. So again, function generator feeds audio amplifier. Output of amplifier positive. Positive will go to one plate of the capacitor. The other plate of the 10 microfarad goes to positive on the tweeter. Negative of the amplifier goes directly to negative on the tweeter, and then this tweeter is hooked up just in plain parallel with this one so that I can have a 4 ohm. The only reason is to have a 4 ohm load. When the effect of me closing the switch is simply going to be shorting out these two leads. Okay, that's it. All right, let's just do it by ear first. I'm going to start out at 10K. Okay. I don't know if you can hear that or not, but you know, these horns are very directional. Should probably lift them up a little bit. Get them both elevated. All right. Okay. I'm going to short out right now. And there's little, I'm shorting it, unshorted. So switch right now is in position 1, now position 2. Very little effect on the output level, which is to be expected. Let's go down to 4K, which is the crossover frequency. And do the same thing. Now we should notice the level drop about in half. I mean, increase by double. That's what I mean. So at position 1, this capacitor is actually attenuating. In position 2, we'll get the full output. So here's position 1. Get ready for 2. It does almost double. 1, 2. The effect should be even more prominent at 1K. Okay, position 1 with the capacitor attenuating by quite a bit. 2, it should be a lot louder. It is. So that capacitor is definitely doing its job. The fact that at 10K it made little difference. We go down to 4, it makes it sounds like it's dropping about attenuating to about half acoustic output just by my ear. You know, you can't really tell by ear, but it just kind of sounds it. But I'm going to go ahead and see if I can take another unscientific measurement with my my Sony here. Now I'm just going to set the Sony. Let me prop it up. Okay. Let's go ahead and I'm going to start out at 10K. Okay. And I'm going to set this to some level. It's running around negative 10 or 11. I want to short this. Before and after, it's roughly 1 decibel different. So, for example, at 10K, position 1, it was like negative 10, negative 9 at position 2. So it was a little bit louder by 1 dB at position 2. Let's go ahead and go down. This is very unscientific, but you know, it kind of makes the point. It's just kind of verifying. Let me go down to let's go down to 4 crossover point. Okay. Okay, I'm gonna wait. Gotta be quiet for this to get stabilized. Yeah, my fridge just kicked on. That's gonna mess it up. The noise. It's hovering around negative 9. So let's go ahead and short it and see what we get. Negative 5. So that's pretty cool. Let me try that. It's pretty close. Let me try that again. Unshorted. Negative 9 dBs. Shorted. Got readings of negative 4 and negative 3 that time. Do one more. Unshorted. Negative 9, that's pretty stable. Shorted. Negative 4. Okay, so negative 4 is the most stable. Let me turn this off and let me show you what I got going here. So, unshorted, which was position 1, was negative 9. And shorted was negative 4. So you can see it went up 4, 5, 6, 7, 8. That's about 5 dB. So plus 5 dB in position 2, which means the capacitor is attenuating by about 5 dB at 4 kilohertz. You know, that's close enough. It was only attenuating by 1 dB at 10K. That's to be expected. Let's go down to 1K. It should attenuate even more than 5, and that just, you know, what we're seeing here is that tweeter dropping off in its crossover region. The fact that at 4K we're negative, it's my dog growling. The fact that at 4K we're at 5 decibel difference is no, you know, again, so is completely unscientific, because I'm virtually guessing at, not guessing, but it's very rough in terms of me even deciding that 4 kilohertz was the crossover point. So you know what, I'm not even, well, I'm gonna take a measurement at 1K. You should just see quite a dramatic difference at 1K as well. Now I'm gonna call it quits here. So let me go down to 1. -1 with the cap. Shorted. Can't even do it because it went over. I gotta lower the level here. Try that again. With the cap. -11 dBs. Shorted. -1. So that's a 10 dB difference. I could run a few more measurements on there just to get it a little more accurate, but it doesn't matter. You can see the point is that down at 1K now we're now the capacitor is attenuating by acoustically by 10 dBs. So you know this is experimentally speaking, our 10 microfarad capacitor is right on the money. So that's all I'm going to do. Go down lower. Okay. There's 2K. We go down a little further. That's 600 hertz. Getting really low now. So you know the capacitor is doing its job. Back to 2K. Okay. Turn everything off. So that worked out perfectly. Experimentally, that's actually turned out to be much closer than I thought it would be using this pretty crude technique. But we've proven experimentally that our calculated 10 microfarads is perfect. So in summary, I'm going to sum it up and go ahead and start soldering this up, trying to do the mechanical connections, but for my own sake, in summary, the schematic is going to look like this. Plus and minus. We have a woofer that is going to be directly wired without a crossover. We have a tweeter that's going to have an L pad. Okay, and these two are going to go to negative. Okay, there's our 10 microfarad. Here's our L pad, like that. So that's going to be the wiring diagram. And mechanically, I've got to get that tweeter to fit. I've got to drill a hole for the L pad. Oh, here's the L pad itself, and I haven't opened all this stuff up yet, but I bought these knobs, hoping to fit. So you drill a hole for this, and this guy's going to come through there. I got the hardware to attach it, and then this will. See if this fits. Yeah, presses right on there, fits nicely. Yep. Oh, cool. It's got that little, that's made for it. It's got that little thing there that goes right into that dot right there to align it. Hey, man, that's cool. I didn't realize it fit that way, so I'll turn it all the way to the left, and then that knob will go on like that. And then that's our level control, 0. It's given it as a decibel scale. So 0 all the way up to infinity. And I haven't never worked with L pad before, so I'm guessing 0 means you're not going to hear anything out of the tweeter. And then as we go up, we double at 3 dB and 6 and all the way up to infinity, which means every bit of signal possible will come out of the tweeter. Holding this too high for the camera. So 0, nothing. So it's pretty cool how that works. You saw that earlier, but there's a little tab there that goes into the... Okay, enough of that. Put this video together, and then I'm going to start with actually physically modifying. We'll start by soldering the capacitors to the backs of the tweeters, and then don't have to drill the hole for this, and I don't know, too tired to think about it tonight. Anyway, at least we figured out the crossover frequency and the capacitor to use, and experimentally verified that it's what we want, what I want, and we'll go from there. Thanks for watching. I'll pick up next time with the mechanical part of this process.